Okay, so today's lesson is topic 4, bigger and smarter telescopes. So, as the topic of astronomy grew and scientists wanted to explore and look deeper into the universe, they needed bigger telescopes. So these bigger telescopes were required to look deeper into the universe. And we did talk about combining telescopes a little bit when we were in our last topic, but now computers are also used. So using powerful computers, it's now possible to combine images from 2 or more telescopes, and that creates the equivalent of one telescope the size of the total distance between the two. So for example here, these are the twin Keck telescopes located in Hawaii. This figure here is showing one of the first really large telescopes by Sir William Herschel, and he was able to discover the planet Uranus with this telescope in 1781. All right, so again, you can take images from 2 or more telescopes and then using computers to combine them into one image. Another thing we're going to talk about here is adaptive optics. So stars, the twinkling we see, it's because of the motion of Earth's atmosphere. It's refracting their light randomly, and that's what makes it difficult for astronomers to get a clear view of the stars. So what's being done is astronomers, they will now connect computers to telescopes to help with that problem. Then the computer program, it will tell the computer to sense when the Earth's atmosphere moves. So that's called adaptive optics. It's the technology that adjusts the mirror of a telescope, or it adjusts the image of a telescope to cancel out the effects of the constant changes in the Earth's atmosphere. And this computer software, it processes the images they make to remove that blurring effect of the atmosphere. Another process that is used here is a way to measure with triangulation the distance to the stars, for example. So this method, triangulation, the parallax technique, it's a method of measuring distance indirectly by creating an imaginary triangle between an observer and an object whose distance is to be estimated. Same method is used by astronomers to measure distances to celestial objects, so using triangles. So you need to know the length of one side of the triangle, which is the baseline, and then the size of these two angles that are created when imaginary lines are drawn from either end of the baseline to the same point here on the distant object. And then we would measure this distance once we've created our triangle on paper using ratios, and then we can estimate that distance to the object. So let's take a look at this example here. Okay, so for example, I had some other stuff typed here. Okay, so in this example, we are trying to figure out this distance here, the distance to this tree. So the first thing we have to do is create a baseline. So you would create the distance here, that's called the baseline. So a long straight line, and you can measure this. And in this case, these two kids have measured it. It's 120 meters long. Okay, so that's just measured with meter stick or whatever. So that we know is 120 meters. So then just mark it off with the 2 stakes. The next thing you're going to do, and I do have videos to show afterwards, is you're going to figure out these 2 angles. right here. So you're going to measure those two angles. You can use the devices like an inclinometer or a protractor. And so let's say the angles measured, which are shown here, are 75 and 65. So I'll just add that on here. Okay. So those are just measured using like an inclinometer, protractor. So 75 and 65 degrees. And then this baseline was measured, and it was measured to be 120 meters long. Okay, so next is to draw the same diagram on paper, but you're going to use a scale drawing. So the scale drawing, we're told, is 1 centimeter is equal to 20 meters. So that's the scale drawing we're going to make. So you would choose an appropriate scale. Okay, so we're going to use 1 centimeter is equal to 20 meters. All right, so if 1 centimeter is equal to 20 meters, how long is our baseline going to be on the paper that we draw on? So you're going to set that up as a ratio. So 1 centimeter is equal to 20 meters, and we know it's 120 meters. How long is our baseline going to be? I'll just call it x. So cross multiplication, 1 times 120 divided by 20, that gives me x is equal to 6 centimeters. So when we draw it on our paper, this is our drawing, our baseline is 6 centimeters long. All right, based on our scale that we chose the scale that 1 centimeter is equal to 20 meters. Okay, so baseline is now drawn. So now all you're going to use is measure this line, because we know our two angles, we know our baseline. We're going to measure this line with a ruler. So when we measure it with a ruler, let's say we get 8.2 centimeters. So using our same scale, that 1 centimeter is equal to 20 meters, we're going to set up our scale. So again, 1 centimeter is equal to 20 meters. When we measured this with a ruler, we got 8.2 centimeters. So what is the actual distance? All right, so again, cross multiplication, 8.2 times 20 divided by 1 gives 164 meters. So that means the actual distance from the baseline to that tree is 164 meters. So triangulating on a star, astronomers will also use triangulation to determine the distance to nearby stars in order to work from the longest possible baseline available without leaving Earth. 2 sightings of the nearby star are taken 6 months apart. Okay, so for example, January and June. Therefore, by doing that, the baseline is going to be the diameter of Earth's orbit. All right, by doing that 6 months apart. So the baseline, therefore, is the diameter of Earth's orbit around the sun. Okay, which is a known measurement. So then when the sightings of the nearby star are made, the star will appear to have moved against the background of the fixed stars behind it, which are much further away. Okay, so this is the star, there's the distant stars, they're going to be used as reference points. So the apparent shift in position of a nearby object when viewed from 2 different points, that's called parallax. And then it's used to provide reference points for measuring the 2 angles. All right, so that's what this diagram is showing. Astronomers will use the diameter of Earth's orbit as the baseline for triangulating on a nearby star. The angle between the baseline and the star's position, it's measured in January and June, for example. And the distant stars appear to be fixed, providing a reference point for measuring the 2 angles. Okay, I'll pause here and we'll watch this video. Okay, so the last thing we need to talk about are the units that we use, so AU and light years. So the astronomical unit is AU. That's the distance from Earth to the Sun, which is 150 million kilometers or kilometers. But because interstellar distances are so much greater than the solar system distances, AU quickly became impractical to use. So astronomers then created the light year. So a light year represents the distance that light travels in 1 year. It's a distance equal to about 63,240 AUs. So for example, the nearest star to Earth is Proxima Centauri. It lies more than 272,000 astronomical units from the sun. So it's about 4.2 light years away. And you can just do that with like setting up a ratio. So like 1 light year, 63,240 AUs. And then we were told it's 272,000 AUs, and then we can kind of estimate how many light years that is. So 1 times 272,000 divided by 63,240, and we get approximately 4.3 light years away. Okay, so I do have one more video to show here. So I'm going to pause.